Hello everyone and welcome to the next webinar series. This is Aparna Deshmukh and I will be your moderator for today's session. We are excited to dive into our today's webinar titled Sustainability in Thermoset Polyurethanes Used in Building Construction. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion of 1 PDH. Your certificate will be available in ACI University under the Certificates tab within the 2 days. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for one learning unit. So let's look into our description for our today's webinar. This presentation will explore polyurethanes, which are versatile materials extensively utilized in construction for applications such as insulation, waterproofing, concrete labeling, and more. It will highlight the differences between thermoplastics and thermosets with a focus on their recyclability, sustainability, and recent advancements in making thermoset polyurethanes more environmentally friendly. Our learning objectives for this webinar are as shown on the screen. Now let's welcome and introduce our today's speaker, Dr. Thomas Garrett. He is a scientist and serial entrepreneur with expertise in sustainable manufacturing, particularly in construction products. He has authored over 50 scientific publications and is the inventor of numerous performance enhancing polyurethane additives derived from natural sources. Dr. Garrett has founded 6 companies globally dedicated to helping manufacturers develop greener and more competitive solutions. We are thrilled to have him with us today. Please join me in welcoming him as we look forward to his presentation.
Welcome, everybody. So we have about 38 slides to go through today on polyurethanes, especially thermosets and some thermoplastics used in the construction field. And today we're going to go over what are polyurethanes, and I'm going to include polyureas and polyisocyanurates in that class of compounds. We're going to talk about what are polyurethanes used in construction, where they are. So what are they? Where are they? What's a thermoset versus a thermoplastic? Or what is sustainability? What makes a polyurethane construction product sustainable? Some problems with sustainability. And I'm hoping time will allow, we can talk a little bit about PFAS because that's a very hot topic in the field right now. And then we'll go through the usual in stuff. So first, I'd like to talk about what are polyurethanes. Polyurethanes were discovered by Otto Bayer in 1937. He was looking for a way around the DuPont nylon patents and came up with a material that is actually not a really great fiber. It's only used in fibers in spandex, but works as a really great rubber. And the Germans were cut off from Malaysia in World War II. And so they really developed this field because they didn't have any other source of rubber. And then after World War II, it came back to the US in a technology transfer program. And our predecessor company, one of our companies, was fortunate to be involved in that program. And so we've been working with polyurethanes ever since. Polyurethanes are polymers, a distinct class of polymers in the sense that they don't start with a monomer and then turn into a polymer. They start out with an isocyanate, you can see here in red, and an alcohol, and turn into a polymer in one step. And if it's done in one step, it's a so-called one-shot polyurethane. And you can see here in red, the isocyanate becomes a urethane link, and the alcohol, the hydrogen moves over here and becomes a urethane, and polyurethane just means it has many of these urethane bonds in it. And some other allied chemistries that happen at the same time are isocyanates react with water. They form this intermediate called carbamic acid, which evolves CO2, and it forms an amine, and carbon dioxide, and this is important to make foams. So a lot of polyurethanes that you're going to see in the construction field are foams because water is cheap, and it makes a lower cost polyurethane, and polyurethanes can be very expensive. Another chemistry that's used in the polyurethane chemical class is for either this amine or a different amine to react with an isocyanate to form a urea. And you can see the difference between a urea and a urethane is simply this oxygen has been replaced with this NH group here. Another chemistry that happens a lot in construction, and I'll show you examples of all this in a second, is for 3 of these isocyanate molecules to turn into isocyanurates. And this is a very important molecule in construction because it's very temperature stable. So it's used a lot for insulation and for when things need to be very temperature stable. And so these chemistries combine to form these kinds of products in polyurethane. Basically, there are cellular products or foams, and these are flexible foams like your mattress or the seat cushion you're sitting on, and rigid foams. And mostly in construction, we're going to see the use of rigid foams. And then there are non-cellular or so-called case applications, coatings, adhesives, sealants, and elastomers. And we're going to see in construction they use a lot of coatings, sealants, and elastomers. Not so much adhesives, although you may have seen this in Home Depot. Gorilla Glue is a polyurethane-based adhesive. But you'll see coatings, sealants, and adhesives a lot in construction. And then in fibers, we're not going to talk about today, but that's what Otto Bayer was trying to make, were fibers. And in fact, it does make a fiber, and we know that fiber as spandex. So where are polyurethanes used in construction? This polyurethanes may not be a term that you've heard before. It's actually used a lot in construction. $29 billion were used alone in the US last year. And these are some of the applications. So one application, as I mentioned before, is rigid foam. And rigid foam is used for a variety of uses. Probably the primary use is for insulation. And so here in the upper right-hand corner, you see spray foam insulation is a very common use of polyurethanes in construction. And here it's sheet stock. So this is prefabricated insulation panel. It's extremely efficient, much more efficient than other kinds of insulation. And so that's why it's used in your refrigerator, because it gives the most insulation per inch of insulating material of any material known. And so if you're doing like a wood deck, you can put this kind of panel over the top, or you can put it underneath your sheetrock. Here you're gonna put it on in a sprayed in place application. Rigid foams are also used a lot in crack filling. If you've been to Home Depot, you've seen great stuff in a can, and essentially this is on the upper left-hand corner, a commercial application of that. This is in a concrete tilt-up, which is never perfect, and so you can make it perfect with spray foam. It's also used for leveling. So if you have some settlement in a concrete slab, why it can be raised with rigid spray foam. Here are some case applications or coatives, sealants, and elastomers used in the construction trade. The first one on the left is caulk. Polyurethane makes a superior kind of caulk. Really, it's up there with silicone in terms of performance. They're the two higher performance types of caulk. It's also used a lot for deck coatings, especially in concrete parking garages and non-slip surfaces. Also to seal. So if you have a deck or a place where you don't want water to permeate through, it's going to be applied as it shows on the right with a roller, and you can put more than one different kind of coat on to get whatever texture you want. So these are the primary applications for polyurethane in the case type in construction. Now we're going to talk a little bit about thermosets versus thermoplastics. And in construction, you're going to see both kinds of polymer types being used, but they're really very different. The primary difference between a thermoset and a thermoplastic is, does it melt after you cure it if you heat it up, or does it burn after you cure it if you heat it up? So in a thermoset, you're creating an irreversible chemical bond. So you have these polymers, which are shown in the black squiggle, and then you cross-link it, and the cross-link is shown with the black dot. And that creates a cross-link polymer. And it's ideal for high heat applications, for chemical resistance applications, for when you need structural integrity, and when you don't want things to deform. A thermoplastic is a reversible type of cured polymer, and you still get basically a pseudo crosslink, but the kinds of things that form the pseudo crosslink, which are shown in the black dots here, are hydrogen bonds or things that can reverse with temperature. So they soften with heat. They can be high strength, they're shrink resistant, and they're a lot more easily recyclable, although we'll talk about that later. So the big difference between a thermoset and a thermoplastic is when you heat it up, a thermoplastic melts, but because you have an irreversible crosslink in a thermoset, when you heat it up, it doesn't melt. And if you keep heating it up, it just burns. So examples of thermosets are polyurethanes, which we're talking about today, but you've also seen in the construction trade epoxies, rubber, as well as silicone. Examples of thermoplastics are nylon, ABS, which is used a lot in black pipe. That's the black pipe that you see on the job site. PVC, which is typically the white pipe you see on the job site. And high density polyethylene, which can be a variety of different colors. Okay, so the title of this talk is Sustainability in Thermoset Polymers Used in Construction. And so we have to define what is sustainability. The textbook definition of sustainability is for people to coexist on Earth over a long time. So what does that mean? Well, sorry, this should be 1 and 2, but I'm going to say that there are 2 principles involved in sustainability. The first is it safe? And the second is it circular? Now, by safe, we're using the precautionary principle, which is known in the Hippocratic Oath that physicians take as first do no harm. Today, that precautionary principle is primarily expressed in low carbon emissions or lower carbon emissions. But what we define as safe really is fashionable. 20 years ago, carbon emissions weren't even on the radar, but we've seen at that time it was no NOx or no acid rain, no ozone depleting chemicals. Then it became nothing toxic like lead in paint. We've seen a national security definition of this. You know, it's not from Cuba, it's not from the Soviet Union. In the past, nothing made with child labor or violation of human rights. So the definition of safe is kind of squishy, and it's different things to different people over different time frames. Today it's mostly lower carbon emissions, and we'll talk about that. The definition of circular is really timeless. And there are 2 definitions of circular. One is the natural carbon cycle. In other words, is it biodegradable? And that is God, or nature, if you will, does the recycling. In The Lion King, Mufasa tells his son, when we die, our bodies become the grass, and the antelope eat the grass, and so we are connected in the great circle of life. And what Mufasa is talking about is simply the natural carbon cycle. Now, technically, we can do a version of that without nature, and that's a technical cycle of recycling, a technical circular economy. And that's when humans recycle their materials. And as we're going to see later, there are some differences, and the government actually, I believe, has a preference towards the second one. Nature clearly has a preference towards the first one. So here are examples of the two cycles. The natural cycle, which God or nature has done very successfully over many millions of years, is that sunlight hits a plant, the plant does photosynthesis, it makes things for the animals to eat. The plant or the animal dies, and that gets recycled back into new plants and new animals through root respiration, and the circle continues. Animals give off CO2. For example, humans, we breathe in oxygen, we give off carbon dioxide. Plants absorb carbon dioxide, and that creates a natural cycle. Of course, we can insert ourselves into this natural cycle, and the factory can make things. It might throw off CO2, which then could be absorbed by the plants, by trees and plants, or we could insert ourselves, as we're going to see later, into that cycle as well. Now, there's a lot of talk about fossils and fossil fuel. The planet wasn't always the same as it is today. There wasn't as much oxygen as in the past. There weren't as many organisms that decomposed products. And so a lot of the original green growing stuff became fossils and fossil fuels. But then the atmosphere of the planet changed from a reducing atmosphere to an oxidizing atmosphere. And so that doesn't happen anymore. And that's why fossils and fossil fuels are a limited resource. We can also have a cycle technically, and technically what happens is that the resin is made, the polymer is made into a raw material, and then somebody manufactures a product out of the raw material. The product is used. If it's recycled into the same raw material as was originally made, that's closed loop recycling. If it's recycled into a different product, that's called open loop recycling. They're both types of recycling, and we're going to see that both types being used. What I want to observe, however, at this point, is that the natural cycle has worked with virtually everything on the planet very successfully, except for fossils and fossil fuels originally. It's now worked very successfully for millions of years, whereas on average, the technical cycle is really only used 5 to 9% on average. Recycled materials are actually recycled only in a 5 to 9% basis. There's one exception to that, which is tires, and that's going to be where the government, I believe, is going to have an opinion. So what makes a polyurethane product, construction product, sustainable? If we use our definition of safe and circular, it's safe and it's circular. And so by safe is that we did no harm in the manufacturing of the construction product or the building of the construction site. And circular means what happens if the building is demolished or when the building is demolished. Now, as I've alluded to a couple of times, sustainability can depend on who you ask. God and nature prefer the natural cycle. As I've said before, it's been extraordinarily successful over millions of years. The technical cycle, what we call recycling, is often preferred by the government. And the reason it's preferred by the government is because they can create something called EPR, or Extended Producer Responsibility. In other words, they can tax it. It's really hard for the government to tax what nature has done over millions and millions of years. It's really easy for the government to say, okay, if you don't recycle your construction products, we're going to tax you. And they're probably going to do more and more of that. And the reason is because when they have done that, as in tires, they get a lot of recycling, something like 79%. But when they don't tax it, they get very little recycling, like 5 to 9%. And so we believe that this is coming. It's probably going to begin more in packaging, things like cardboard, but it's eventually going to extend probably to all manufactured products. When you talk about levels of recycling, there are really three broad terms used in the industry. One is cradle to gate, one is cradle to grave, and one is cradle to cradle. In a cradle to gate life cycle assessment or sustainability analysis, you're going to make the product and then you're going to measure its sustainability to the gate of where the manufacturer is going to make the construction product. And that's a cradle to gate analysis. And most life cycle assessments are cradle to gate. And the reason is the manufacturer can't control how the product is used. It can't control whether a building is going to be demolished when it's done. It can't control how the product will be used on the job site. And so when you're comparing apples to apples from different manufacturers, you often see LCAs or life cycle assessments or life cycle analysis, and those are almost always cradle to gate. And they work very well for a difference analysis, but probably not very well in terms of a circular cycle. In cradle to grave, basically you're going to analyze the manufacture of the product all the way through to when you landfill it or recycle it. And many regulatory authorities, like the EPA, prefer cradle to grave. And the reason they like that is because the regulatory authority is concerned that in the grave portion, that something bad is going to happen to the environment when the product is disposed of. So cradle to grave, you see that often with regulatory authorities. Model code agencies, especially in the more developed countries, prefer cradle to cradle. And cradle to cradle is how circular is it? They, like LEED and the US Green Building Council, prefer cradle to cradle because they want to see the product reused, and that's really a measure of its sustainability. Which cycle are we in, natural or technical? What percentage of it is being recycled? Is it recyclable? Those are all cradle to cradle analyses. As I said before, the natural cycle has been very successful. The minimum one, the technical cycle, it's theoretically possible, but it's had really minimal success. When you get a construction product, or really any product these days, you often see on the back a logo. And the logo will have letters or a number and this little recycling symbol in it. And if it says PA, it's a nylon, because a nylon is in a part of a chemical class called polyamides. If you see 07, that's the ABS, like in the black pipe. If you see a 03 or the letters PVC, that's a PVC product, and it can be recycled as well, although not very much is. HDPE is more of a success story, and the success story is 5 to 9%, and that's a 02. In this case, it's a high density polyethylene. This is an example of tire buffings or tire regrind, and it's a much more successful technical recycling, although it's an open loop recycling. And we do some of this in our rubber coupling products that we make, is that we take regrind from a tire buffing operation or a tire regrind operation, and then we open loop recycle it into a coupling used on a job site, mostly for high rise. If you've seen those rubber couplings in high rise, that's that product, and that's about a 79% recycling in the U.S. Okay, so we've talked about the technical cycle, its successes, its failures, how the government is probably going to tax more in order so that it can have more revenue, and also so it can push us towards success. But you can also have enter the natural cycle, and this is an example of recycling using the natural cycle for thermoplastics. And this comes to us from Pekorsky's group at University of California, San Diego. And what they did was they take polyurethanes, which can also be made in a thermoplastic way, and they used two different strains of bacteria. They put the spores into the polyurethane, and as you can see, over time, they dissolve. And so God is recycling these thermoplastics. And this is really exciting, groundbreaking stuff, and very novel, and a way for a thermoplastic, like thermoplastic polyurethane, to enter the natural cycle. Polyurethanes can be made both into thermoplastics and thermosets, although they're mostly made into thermosets. There's one problem with this, in my opinion, and the problem is that we think that in construction products, most customers don't want dissolving buildings. They would rather not have their buildings fall apart prematurely. They'd rather have the building last a long time, and then when it's demoed or landfill, then they want it to dissolve. Then they want it to fall apart. They don't really want it to fall apart while the building is being occupied. So while this is really exciting and very novel, I'm not sure how much use this is going to have. We'll show you a different way of approaching this. This is what I talked about before, where we're taking tires and recycling them into couplings, and that's an example of the one of the couplings that I was talking about. This one in particular is a below ground coupling that's used in plumbing, but you can also see with the metal shield there the above ground coupling used in high rises. Okay, so how could we theoretically enter the natural cycle with a thermoset? Because it's not going to fall apart, it's not going to dissolve, because that's what thermosets do. In fact, if you heat it up, it won't fall apart, it will burn. So how conceptually could we design a molecule that lasted a long time but fell apart when we wanted it to? And we've done this in two ways. The first way is that we take basically this molecule here and react it, use it to cross-link with lignin, which is the glue that comes from trees. Trees are about 30-40% cellulose, 30-40% glue or lignin, and then the rest is sugars and things like that the tree needs to live. Anyway, this is tree glue. And so if you have a cross-linker like this on tree glue, like this moiety here, this functional group, then you have something that has that the bugs can eat, the bacteria is used to eating, the tree glue, and something that is going to make a polyurethane thermoset crosslink. We can also do the same thing with soybean oil. We take soybean oil, which is this part of the molecule, we add this crosslinker on this part, and this molecule now can make a thermoset polyurethane here through the OH group. Here it's through this NH2 group, and form a cross-linked bond. But this part is something that the bugs will eat. And so when you landfill it, it slowly dissolves because the bugs can get a handle on it on this part, but it doesn't dissolve in use. And so we think that this is maybe a better way to make a better product that will last a long time in construction, but then if the customer chooses to landfill the building, rather than pick every piece of the building apart and try and recycle it, nature will make this product sustainable. So this is our first research stream. It's with soybean oil. Soybeans look like this. You may have had them, or you may have had tofu, which is the protein made from soybean. That's the primary food that comes from soybean. It's about 40% of the bean. About 20% of the bean is oil, and it's that oil that we then take on to make the product that I showed chemically in the last slide that can be a sustainable building product and a thermoset and last a long time. This is our second research stream in our labs. We take trees and we take the lignin out of trees. The cellulose is made into paper, and we take the 20-30% lignin, which is the binder or the glue in the tree, and we put that cross-linker on, and now it can cross-link and make a cross-link polyurethane, a thermoset polyurethane that nature can recycle. Okay, so the primary definition, as we talked about, for safe these days is lowered carbon emissions. And depending on whether you use the soybean or the lignin form, for every ton of what we call honeybee, which is the sustainable raw material used in polyurethane thermosets, we think for every ton we're going to suck out a ton of carbon from the atmosphere. So when you use this product in a construction application, it will automatically lower carbon emissions. Our second definition of sustainability is it circular? And it is circular. Honeybee is USDA bio-preferred. You can see that it's about 91 to 94% organic carbon. And we've taken it and put it into, well, sewer water. High biological oxygen demand environments is the polite way of saying sewer water. And what we see is that the physical properties do not decay very much, but the mass starts to decompose. And that's exactly showing what I showed in the chemistry slide, that it's going to last a long time in a building product, but enter the natural cycle. Now, I'd like to talk a little bit about crops, because there are some experts in sustainability that are concerned that turning crops into sustainable materials is bad. They believe it's bad because it means less food, or that we're cutting down forests, and therefore it's going to be less sustainable in the end than mining or chemistry or something that doesn't touch the food chain. And there are a couple of points I'd like to make about this notion, which has come up in sustainability. The first is that crops have been around for 13,000 years, since the agricultural revolution, and we've been making construction products and food out of plant material for approximately 100,000 years. And plants and trees have interacted with the planet ever since, just before it became an oxygenating environment, for about 250 million years. So we think that these are long times. And so we think that this meets the definition of sustainability. So we think the right question is not, does a process use a crop as a raw material? We don't need to be afraid of it. The right question is, does a process create more and cheaper food, or more and cheaper planting of green things, which absorb carbon dioxide? As I showed before, the part of the tree or the part of the bean that we're using is a small part of it. And so we're effectively subsidizing the protein in soybean oil, or subsidizing the maker of paper, or subsidizing the planting of trees and plants. Okay, we've talked about the problem with sustainability from a government and tax sense. I'd like to talk about the problem with sustainability from a customer sense or a perception sense. People believe that sustainability costs more and delivers less. So that sustainability is synonymous with, I got to pay more, but I'm not going to get as much. And in part that's true, because who's going to pay for sustainability? Well, the customer's going to pay for it. Maybe the customer is going to pay for it through increased taxes because we're going to bring out extended producer responsibility, or we're going to bring out cap and trade from the government. Or maybe the customer is going to pay more for it because he's going to have a LEED platinum building, and that fancy LEED platinum building it's going to cost more than a not LEED platinum building. We'd like to propose a third approach, which is the customer gets a benefit for sustainability instead of a cost. And so we'd like to propose the notion that sustainability makes the most sense when there's an improvement in performance. For example, improved fire, smoke, and toxicity. And let me show a couple of examples, or one at least, of what I mean. So this is a video of polyurethane rigid foam of the type used in construction with no flame retardant added. And this is a German fire test, a DIN test. And as you can see, that when you put a flame on polyurethane, if there's no fire retardant in it, it goes up like a house of fire. Making it perhaps less than ideal as a construction product. So what people do is they put in a flame retardant. And this is a video of the same German standard test being done with a flame retardant in there. And the flame retardant is called TCPP, and it's a chlorinated phosphate. And as you can see, what happens is that the material develops a char, and once the flame is removed, the char stops the material from burning. You have to wait a little bit. Here it comes. And it's off. So as you can see there, the flame retardant stopped the burn once the flame had been removed. The problem with TCPP, the problem with this flame retardant, is it's toxic. And so the government is probably going to eliminate it, even though it's what makes polyurethane, rigid polyurethane foams, a good construction product. So here is the same test with our technology. This has no TCPP in it. No of the toxic flame retardant is not in the formulation. Instead, we've put in our sustainable materials. And now watch what happens. He puts the flame on it. It starts to burn. And I want to stop it here because look at this. It's going out. The flame is going out with the flame on it, with the burner on it. So that's an improvement in performance by using sustainable materials. And we like this notion of, instead of taxes or bragging rights, maybe we could give the customer more. And if we could give the customer more and make it sustainable, why then the customer ought to be willing to pay for it because they got more. So in conclusion, what you can see is that the use of novel polymer chemistries can harness the natural cycle and improve performance, making polyurethane construction products both sustainable and worth it because they're higher performing. Okay, I think I'm okay on time, so I'm going to go into the bonus round, which is the current problem we have with PFAS. And PFAS stands for per and polyfluoroalkyl substances. And one of the problems we're having with PFAS is that PFAS means different things on different continents to different people. In the US and Australia, to normal people, to the layman, PFAS means dangerous, small molecular weight, water-soluble molecules on an alkyl chain, such as PFOS or PFOA, that cause liver damage. And they're forever chemicals, and they sit around and they cause liver damage. And both the US and Australia are studying these materials, and lawsuits have already run into the billions of dollars. And to a chemist on any continent, by definition, a per or perfluoroalkyl substance would include fluoropolymers such as FKM. I'm going to explain in a second why would you care about that. In Europe, the regulators are maxing out. They're saying anything with a carbon-fluorine bond we're afraid of, it's toxic. Where the economy is really important, we'll write some exceptions, but basically we're going to make the carbon-fluorine bond illegal. Now, we think that that's ridiculous. My apologies to government regulators on the call, but we don't think you have to do that. If, for example, you want to make FKM, which is a very useful building material, I'm going to show that in a second, you're going to take two monomers, VDF and HFP, these two here, and you're going to do an emulsion polymerization. And the dangerous thing here isn't the product. The dangerous thing here is the surfactant that you had to use to make the product. And the key is you didn't have to use it. If you took out the PFOS, you could still make this product. It just costs a little more. And the reason that matters is because long molecular weight molecules, like most polymers, are not toxic. There's a thing under the TSCA law, the TSCA, Toxic Substances Control Act, called the polymer exemption. And the polymer exemption basically says we know most polymers are not toxic. So this thing isn't toxic. FKM isn't toxic. What's toxic is whether or not you optimize the reaction by using the surfactant. Okay, I talked about why FKM would be useful. So these are buildings in New York City, 10 and 30 Hudson Yards in New York, and they got LEED certification in part by using fluoropolymers in their coatings. The use of fluoropolymers reduces VOCs, it saves on CO2, it extends the life of the building, and then therefore you don't have to paint and recoat buildings. As I said before, suppliers can produce FKM without the bad surfactants. Whether or not they do is a normal matter. Now, we've done some testing here, and we believe that people who sell FKM in the US, Europe, or Australia have eliminated these. Solvay in particular is very good about this. They've eliminated this product that causes adverse human health effects. We believe China keeps it in because China sells mostly on price. We're absent of data in India. We haven't done any studies on the India stuff. As I said before, we do not believe that fluoropolymers have to be eliminated from construction products because the polymers themselves are not going to be dangerous, and that's why there is a TSCA exemption. I'd like to acknowledge my coworkers who did the work that I talked about today. Frank Dew in Kansas is responsible for much of the soy work. Saeed Foshat, Sashi Gadam, and Swarup Maiti responsible for the lignin work. Indulis Gruzins did some initial work in Kansas on filler and resilience that make these things so performing. Working with Tommy Catherine and Julie Clayhammer in Paris on the LCAs, and I've worked with architect Bill McDonough, formerly Jay Bullis was there in Charlottesville. We're really the inventors of the cradle-to-cradle notion with chemist Michael Braungart. Some references. This is our research. You can mostly in the patent literature, but also in the we have publications. These are the references for the other stuff I've talked about, including the fluoropolymers and some of the sustainability. Okay.
Yeah, so I request all the participants to please write the questions in the question box. Thank you so much, Thomas, for the great presentation. It was outstanding. You talk about various aspects of sustainability from different perspectives, and that was really wonderful. We are waiting for few questions. We have our first question is so you talk a lot about sustainability and the government role, but for manufacturers and end users, how can we get more involved and get to know about the product which is more sustainable or not sustainable?
That's a great question. There's a lot of what they call greenwashing in this industry, where people buy a logo and they stick it on the product and they say, okay, this is green because it has a green cross or a green logo. I'm not trying to disparage the green cross people, but I've seen people say, okay, the cheaper product is more sustainable, even when it comes from the oil well. And I don't see how you get into a endless loop, a circular situation with something that by definition is not circular. So, in a world where people are claiming oil well products are sustainable, there's certainly a lot of blah, blah, blah around there. In the construction trade, I think that Cradle to Cradle and LEED, the U.S. Green Building Council, are probably the leaders in trying to get to the root of the thing. But also, I think you can look and see, what are the credentials? What are the people doing who are selling these products? And, do they have publications? Do they have paper? Are they authentically sustainable? Are they entering the either the technical or natural cycle completely? Or, do they have a green logo on their stuff and, it comes from an oil well? Um, that's phony baloney. That's greenwashing.
Okay, great, thank you. Our next question is, what do you think is the government's role in making them more strict for the use of these polyurethanes as a sustainable material?
So I'm gonna take that in two parts. The first part is what is the proper role for government, and if you believe in a world where green always costs more and it never brings any benefit, then the government's role is to force everybody to do things, either by regulation or taxes or some combination thereof. If you believe in the world that I believe in, which is that you can make a product sustainable and higher performing, why then economics will drive sustainability, and the government doesn't need to have a heavy hand. So I think it depends on which what your vision is, what road you're walking, what's your belief. In terms of polyurethanes in the construction field, as a separate question, I think that that's growing at or above GDP. So I think we're going to see more and more polyurethanes in the construction field as time goes on. It's really the king of all polymers. It can be as hard as the hardest plastic, as soft as the softest rubber. It can be a thermoplastic. It can be a thermoset. It can be a polyurea. It really makes a superior grout. There's a lot of videos on the internet, a lot of reels on that. It really makes superior products. So I think you're going to see more and more. It's the best insulator per inch per inch. So I think it's going to grow. I think we're going to see more and more of it.
Yeah, great answer, Tom. Great. Yeah, so the question is, as a new engineer in this building construction side, how I can gain more information or knowledge regarding using sustainable construction products? Is there a code or a manual which I can refer to?
Yeah, the code is with LEED, the U.S. Green Building Council, and the best manual or judge is MBDC in Charlottesville on whether or not it's cradle to cradle. After that, you're kind of up to the manufacturers, and we approach this from I think a pretty nerdy point of view because of our background as chemists.
Hmm.
But in terms of what meets the street, that's really the best stuff. I wouldn't necessarily go by the stickers on the product. That's probably not the best way to go. Um, if you're going to specify a lot of something, then I think you want to look into the manufacturer's credentials. What I'd like to see is a pull from the market. I'd like to see that engineers and architects see products like ours, which are more sustainable and higher performing, and they specify those. But naturally, I'm a little biased.
Great, thank you. So the question is like, if we go to, you talk about cradle to grave and cradle to gate. So are those studies available to check on or refer to? And how was those studies performed?
So every study is a little bit different, and they're all performed a little bit differently. And the methodology kind of, the secret sauce sort of exists in that organization. So right now we're doing a study with Greenlee in an LCA study in Paris because one of the competitors said that an EPDM product was more green than a silicone product. Silicone is the second most silicon metal is the second most abundant element on the planet, and silicon comes from sand, and in the end it turns into sand. And we're going to run out of silicon when we run out of planet. EPDM is an oil well product. It's
Mhm.
made by Ziegler-Natta chemistry from oil wells. So by definition, it's not sustainable. Furthermore, a silicone product can be used many, many times, and a EPDM product typically gets thrown away after 3 to 6 years. So it's a life of the vehicle versus a life of the product. So it's absolute greenwashing, and so we're doing a cradle to gate study on side by side an EPDM hose versus a silicone hose, and then we'll publish that. So when you look for an LCA, number one, look to see if it's been peer reviewed. Is this a publication where peers have looked at it, either in the patent literature, it's undergone scrutiny by the patent office, or in a publication that's been peer reviewed, or is this just yak, yak, yak coming from somebody who wants to sell something? So ask for the study and look and see, is it published by a reputable journal? Has it been patented by a real country like the United States or Germany, or or not?
Mhm. Great, great. Thank you. One last question. So you talk about carbon emission, but can you please explain uh, the difference, like how much is the carbon emission with the regular polyurethane and one which is more sustainable?
Great question. So I showed a slide. Let me go back and okay. So on this slide, you can see that these bars are negative.
Mhm.
So a ton of carbon is removed from the atmosphere for every ton of honeybee used, whether it comes from the the soy hive or the lignin hive. Um, in a conventional polyurethane product that comes from the oil well, these would all be positive numbers. So it's going to
Wow.
put carbon into the atmosphere, not take it out. And the reason is because you're going to have to use carbon to manufacture the product, to transport the product, to get it to the job site, and all those things are going to require carbon emissions. And that's assuming you don't look at, you don't begin with the plant. That's
Mhm.
assuming you begin with what's mined from the ground. Um, I'm not always sure that's the best way to do it because, nature has put a lot of energy into that oil, and we're not counting that. We're counting that as zero. I'm not sure that's the right way to do it. But basically, if it's conventional polyurethane products, put carbon in the atmosphere, ours take it out.
Okay, great. Thank you. Our next question is describe the differences between one and two-part polyurethanes.
So a one part polyurethane is, let's go back to the beginning slide. Okay. So all polyurethanes are going to be um, made by this reaction. If you do it all at one time, it's called a one shot. The other way to do it is to do a little bit of this reaction and make what's called an isocyanate terminated prepolymer, and that polymer is then cross-linked later with an amine or an alcohol, and that's called a prepol, or not a one shot, a prepolymer reaction. I want to distinguish that between a one part and a two part. In a two part polyurethane, you're going to have two tubes or two buckets that you're going to mix together, an isocyanate part and a polyol part, and you're going to mix those together in the field to make a polyurethane.
Mhm.
You can also have materials that are one part polyurethanes, where basically you've made a polyol, but you haven't cross-linked it yet. And what's going to happen there is that the isocyanate is going to react with water. It's going to form the amine. The amine is going to react with isocyanate and form a urea. And so in that, you're absorbing water from the environment to cross-link it with a polyurea. And that's a one-part polyurethane. You see that a lot in coatings, and it's very moisture and temperature dependent. So when you're on the job site and you're working with polyurethanes, you really want to look at the dew point and what the manufacturer of the polyurethane has to say about the dew point, because it's really going to affect the cure rate of a one component polyurethane. And if it's above a 60-degree dew point, it could negatively impact the cure rate of a two component.
Okay, great. Thank you. One last question. So, what will be your advice to the manufacturers and the owners um, to produce more sustainable polyurethanes?
Um, so my advice would be open. When our customers, who are mostly manufacturers, come to us and they're willing to share their formulas in secret under a non-disclosure agreement, and work with us on a research project, we almost always get them to where they want to go.
Mhm.
And where the manufacturer wants to keep everything secret and doesn't want to work with us and doesn't want to tell us what he's doing, why it's really harder to work with people like that, because they're not being open, and you're trying to help them and you're trying to get them a higher sustainable, more performing material, but let's face it, they're not telling you anything, so you're guessing.
Mhm. Yeah, great, great. Thank you so much, Tom. It was wonderful presentation, and you also handled the questions so well. I think the participants are happy with the answers. So with this, I'm going to share my screen. So with this, we end our webinar. This is our upcoming webinars. Please don't forget to register for our upcoming webinar for February 4th and May 6th, and there will be more added to the list as you go. So please visit aciuniversity.com to register for our upcoming webinars. And with this, thank you so much. Thank you, Tom. Thank you, participants, for attending next webinar and ACI. And if you have any questions, do visit our website www.nonmetallic.org and American Concrete Institute at www.concrete.org. Thank you so much. Bye bye.